Well, hi folks, it's Cliff here, toolmaker from New Zealand. In this video I'm going to go a little bit more deeply into using a surface grinder. You might have seen my recent video, Surface Grinding 101, which was an introduction into using the surface grinder. On this video I'm going to go up a level, maybe using a surface grinder at an intermediate level where I grind up this little gauge. So I'll harden and temper that now before I grind it. You can see in the bottom of the little furnace there's a tile I cut to size because the old one had broken up over time. I don't know if that'll work or not. I ordered this special aluminium silica board, which is probably better suited to it. But while I was waiting for that to arrive from China, it cost $40. I saw these in the hardware shop, these tiles, and they're only $1.50, so I thought I'll give that a try. I don't know whether it'll handle the heat long term. Let me know in the comments if you know about these things. Alright, we've got that bit of gauge plate at 800 degrees C, and we'll quench it into canola oil. Shouldn't take much to harden it, because it's only 1/8 of an inch thick. It'll chill off pretty quick. The moment of truth. So I'm sort of rushing because I want to get out, but it's pretty easy to harden gauge plate if it's thin section like this. No, that's glass hard. Excellent. So we'll just temper it down to about 200 degrees now, just to make it a bit tougher. So I'm going to surface grind this gauge that I've just hardened, and if you saw my Surface Grinding 101, where I explain that the magnetic chuck is ground parallel to the XY slideway, and it's such a fantastic system because any part that you stick on it, put the magnet on, you can then grind it flat and parallel, flip it over and grind it flat and parallel. Well, that information is good for a 101, but actually it's not that simple. A thin part like this is likely to be buckled, especially in heat treatment, and if you put it on the table, I don't know if you can see it there, I think you can just see that it's rocking. It's curved, it's convex on the bottom and concave on the top. And so when you put the magnet on, it's likely to pull it flat, or at least a little more flat than it was before the magnet was on. So then you grind it in that distorted state and grind the other side, and you take it off the magnet, and then it goes back to being buckled and like a banana again. So you haven't achieved what you wanted to achieve. The system of the magnetic chuck breaks down for long parts and thin parts, and you have to be aware of those sort of pitfalls and grind it flat by another method. So here we're holding it in a grinding vise or a toolmaker's vise by its edge so that it's not being distorted, in order to generate that initial flat surface, and then we can put that flat surface on the magnetic chuck and grind the other side parallel. One of the most critical things with surface grinding is the surface grinding wheel. You need to have the correct type of grit, the correct size of grit, and the correct type of bond that holds the grit together, and have the correct type of dressing to dress that wheel so that it is sharp and cuts freely. There's a lot in that, and it's probably the most important thing to know about surface grinding. I can't cover that in one video, but I'll sort of introduce it very roughly. So if you look at this outer diameter of the grinding wheel, and we do a drawing of it, say 20 times full size. So this is the diameter of the grinding wheel. Now we can start to see the little grits, for example aluminium oxide little grains, and some of those end up orientated in an ideal position to act like little cutters, and they cut out little shavings of swarf. Now you want to dress the wheel so that you end up with a lot of these very sharp little cutters pointing down on the outer periphery of the wheel. If you dress the wheel wrong, you end up with this situation with blunt little grains or shattered little grains, and it won't cut very well at all. Or when it gets blunt, they'll have all little flats on here, and in between the grains it'll all be clogged up with metal particles. So there's a lot to getting this right. You need a very sharp diamond. Let's say this is your diamond. A sharp diamond will be much more effective than a big rounded blunt diamond, because what that will do is just put a flat on your little grains. But of course this is difficult to find a diamond that's sharp and stays sharp. They very quickly blunten down, and so it's difficult to get a sharp diamond. It's difficult to get exactly the right grit, type of grit and size of grit. It's difficult to get the right bond. And so to optimize all of these aspects takes a lot of learning, a lot of trial and error, and a lot of analyzing what you're doing. I can't give you all the answers in one short video, but these are some of the things to be aware of that make the difference between effective surface grinding and very difficult, ineffective surface grinding. This is a typical blunt diamond, and you can see it's not very sharp at all. And you can get round that by tipping it over on an angle and trying to use a sharp edge, which is better than nothing. But I find it's even more effective to use a dressing system that is a whole matrix of very small diamonds buried in a weld of bronze, so that because the diamonds are small, they are sharper, and then eventually they wear or fire out, and then you grind down and find another little diamond which again is small and sharper, or you turn it round and find the edge of a diamond that is small and sharper, and you're more likely to strike a sharp edged diamond by that method than you are by using a big single diamond. The other thing is really important that I didn't mention is the right grade of cutting oil that lubricates the dressing and the grinding process is also critical. It's surprising how important it is. You wouldn't think it would be that big a deal, but the right grade of cutting oil helps with the dressing of the diamond, dressing the wheel, and grinding the steel as well is really a big part of successful grinding. Oh man, I just had a bit of a fright. I've been for a walk in the rain and I was a bit damp, my feet were a bit damp, and when I was holding the machine hand wheels I felt a sort of like a needle stab in my fingers and thought, is that an electrical shock? Or is that a static charge? Or anyway, I thought I'd better check the earth. So I went down and followed the earth circuit through. It's pretty basic. Followed the earth wire into the motor housing, and it was just cut off with a bit of insulation tape over it. So the machine was not grounded and not earthed, and I've been using it for 50 years with no earth connection. Oh man, I've just rehooked it up now to earth and checked it, but that's scary. So that factory in Taiwan didn't bother, or the importers into New Zealand didn't bother getting it earthed and checking the earth, and I've just trusted it all these years. Don't trust your machines are earthed, check them. I'm going to go through and check all my machines now. And then in addition to all those factors, there's also how deep a cut you take with the diamond and how fast you traverse. If you traverse very quickly, it dresses the wheel so that it cuts freely and exposes a lot of nice sharp grains, but it gives a bad surface finish. If you dress the traverse very slowly, it's more inclined to blunten the grains and gives a good surface finish. So all of these factors are compromises, and you have to learn where the right balance is. So you can see there, I was grinding it convex at the top, and it's taken 12/100ths, 4 or 5 thou to get it reasonably flat. It's still not quite cleaned up, but I don't want to make this too thin. But if I'd stuck that down on the magnetic chuck, it would have pulled fairly flat and ground the part parallel, but a parallel banana. Now we can put that ground flat surface down on the magnetic chuck and grind the other side parallel to it. But there's a risk here as well, because the part is hardened steel, it very quickly bluntens the wheel, and if you grind the surface of a thin part with a blunt wheel, it'll stress the steel and cause it to buckle once again. So you need to be aware of how sharp your wheel is cutting. Use the right type of coolant, the right type of grain of wheel, the right type of bond, and be aware of not producing grinding stresses. There you can see just how buckled the part was. So now I've set the part up in a grinding vise or a toolmaker's vise to grind the right angle by flipping the vise over on its side. And I'm going to plunge grind in the middle of the wheel. Go back to our drawing here. So when you're traverse grinding, the first few millimeters of the wheel is the part that does all the work and breaks down and becomes blunt or clogged. And so the middle of the wheel, this portion here, is pretty sharp and good. You haven't really used it much. So I'll plunge grind down there using the middle of the wheel until it is parallel and cleaned up, and then just do a very light traverse grind which generates a more accurate surface. So the plunge grinding is good for removing metal, and the traverse grinding is good for generating accuracy. Now, because this is a gauge, it needs to be accurately square, and just checking it with an accurate square doesn't really tell you how square it is. You nearly always see a very fine triangle of light under the blade of the square, and you don't really know whether that's 1/10 of a thou or 1/2 a thou. It doesn't give you a measurement. You really need a squareness comparator for a measurement. I've done a couple of videos on these subjects. If you look on my playlists, metrology, I make a couple of master squares and this squareness comparator. It's just a base that accepts the dial indicator, and you can use it as a comparator and set a dial indicator to 0 there. So I'm on 0 because it's touching off on that nose piece there and on the dial indicator off the master square. And you can turn the master square around 180 degrees if you're worried your master square's not accurate, and average it out. So I'm just shy of the 0 there now, using that master square and squareness comparator, and now I can come up to the edge of the gauge. Oh, look at that. That's within a micron or so of square. So that gives an actual measurement, not just a triangle of light, which may or may not be a small amount. To set the angle, I'm just clamping it against an angle plate with that screw and using a sine bar that I made a while ago, and just using trigonometry and some slip gauges to set that up accurately at 45 degrees. Just curious how accurate this 60-30 square is, you know, the one in that set. I think it's just a cheap set made in China. I wonder how accurate it is. So I set my comparator to 0 there, and let's see how square it is. I could also check the angle. Yeah, it's a little bit out. I'm over on an angle. Let's have a look. Yeah, 5 or 6 microns out. A good 1/2 of a millimeter out of square. I don't know if it's worth setting it up and regrinding it and redoing the angle. It's quite time-consuming work for the sake of 1/4 of a thou. I just need to remember it's not perfect. It's probably fine for most jobs. But, you know, if I'm feeling keen sometime, I could set it up and take that little bit off. Well, thanks for watching that video. I hope you found something useful there. Please remember to like and subscribe if you're not already. Stay tuned for the next videos.